When I say, for example, sometimes when you come, Huda, let me give you an example. You have seen CT images, right? So, how does the image look to you in pediatric cases when we consider the dose? If a high dose is given in a CT image, the image will be very clear and you will feel that the image is excellent. However, you may find that the details of the abdomen and intestine are not distinct, making it difficult to perform resistance. If you always give a high dose for the patient means high count or high detection. In this case, what happens is that the image is very clear, which means your detection efficiency is high. But what about the resolution? For example, in cases like CT urinary tract imaging, you might say that the dose doesn't matter much. On the contrary, with a CT dose, you might see the stone because I am dealing with an object that has high density, allowing me to achieve resolution or see the gravels present in the kidney. So, at this point, with a high dose, the image is very clear, but the resolution itself decreases. That's why you will find that when you increase the dose parameter, you increase the detective quantum efficiency, but the resolution itself diminishes. This explains why in the case of resolution, one value is lower when the dose is reduced. If you increase the value that you are taking, in this case, you won't enhance the resolution. Instead, you will increase the sensitivity of the imaging blade. This will reduce your resolution. The idea of SNR is a relationship between two things: the signal-to-noise ratio of the input and the signal-to-noise ratio of the image produced. There is something called contrast ratio, and SNR. For an object, if you take a region of interest and look at the still counts coming from it or the still counts of its field unit and then calculate the mean value, this represents the signal for me. Now, when I say that this region of interest has a certain variation, how much standard deviation does it have? Do all the pixels in the region have the same value, or is there a difference? If there is a difference, then the variation is high and the noise is high. Therefore, the value of the standard deviation here represents the noise. So, the signal to noise ratio for this object is the ratio of the signal. Here, in summary, if I'm talking about high values, it means that I have a high parameter because there is no variation between the pixels. The SNR is high, meaning my signal is high compared to the noise, and the noise is low. Therefore, my light is high, unlike in examinations with lower resolution. Why exactly is your SNR low? Perhaps why? Because the value of the noise affects the representation between the pixels, and you can create a distinction between the existing pixels. That's why, for example, if you mention a value that is very significant, if it increases, you will find that the image becomes smoother. When you look at the value of your SNR in the images, you find that when it increases beyond a certain value, the image becomes very smooth. If you increase the scan time or the imaging time, the image will give you a high SNR, but it won't provide high resolution. You will find that the SNR value decreases with small lesions and low doses. With the low parameters, what I'm saying is that even in the market, you will notice this, and you will find it present with you. Thank you. There is digital radiography, or 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 digital radiography. We have now entered a new improvement where we will remove this completely, and instead we will use something called a material that generates charges which will be Boston. And we will start with this. There is a need for something called amorphous selenium, or a thin film transistor, TFT panel, which begins to translate the collected charge that has formed, which will be an indicator of the intensity of the incident radiation. It then starts to produce the image through this. This is direct conversion or direct digital radiography. The indirect method can be either virgin or direct digital radiography. I use the same scintillation material or scintillator material, but I don't have the idea of the reader and all that. Instead, I will use something called CCD, or charge coupled device, and I have the TFT, which is the thin film transistor. Now, let's go into details.
In this video, we will talk about digital radiography systems. 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 Open radiography can be eliminated in order to replace it with designs known as charge-coupled devices, CCDs. The user inspection organizations consist of a set of 3 initial steps: the user inspection step, the lower user inspection step, and the user step, where user inspection steps transform into user steps. The user inspection step is nothing more than the user step, which is why it is called the user inspection step. Every photon that makes an angle creates a small chance of survival. Unfortunately, one of the mistakes in using the angle is that it produces the angle in an isotropic manner, or uniformly everywhere. The type of isotropy for this angle maximizes environmental resistance, because the moving angle has a greater value than the angle used for the angle convention. Simply put, the bottle produces a small piece for each image. The bottle contains either ionic glass, cesium iodide, or chemical substances, gadolinium. Cesium iodide is preferred over gadolinium because it can be produced at very low costs. These little rectangular cesium iodide ones make a car more powerful. The diode operates by converting the existing photons from the diode level to an electronic change. Electronic imaging, or electronic, that is produced through the photodiode angle and then converted to the deflection angle or the deflection angle. The pixel detector is a sophisticated device that includes a matrix composed of numerous very small elements. These elements are crucial as they serve as the active components within each detector element layer, DEL, playing a vital role in the overall functionality and performance of the detector system. Resistance to obtaining the electronic volume that is produced through the things that are 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 produced through the things. To manufacture a radio programming system, the level of coverage is determined by the users in the key area everywhere. The fill factor is from the DEL to the active pixel. The relationship between the fill factor and spatial resolution is that when the area of the active pixel increases, it occupies more space in the DEL. The spatial resolution area increases. It has been confirmed that as the active area increases, it takes up a greater percentage of space within the DEL, leading to an increase in spatial resolution. The cooperative company, or the CCD organization, is the other type of digital radiography without a cassette. CCD devices differ from thin film transistor, TFT devices, in that there are no dedicated assistive or specialized aids. The support systems within the CCDs assist all support functions of the CCD using either organizations or fiber optics. The translators for many subscriptions to the channel can enable the charge-coupled device, CCD, to convert light photons into electronic signals, as well as send the electronic signals to the computer for processing. The latest cassetteless digital radiography system is the Transformative Radiography System, or the latest cassetteless radiography system. This advanced system is equipped with a highly efficient semiconductor that is specifically engineered using high-quality selenium materials. This system operates using a higher level development for the upper side of 2 minutes before the X-ray is allocated. The collaboration between the high-level X-ray photon and the higher level leads to the development of the higher level, causing further repeated development. This final image provides a different perspective of each type of radiographic system without a cassette.
I don't think we need an explanation, so that's it. Your explanation is important, Dr. Islam. No, really, the video is actually nice, mashallah. I mean, he even made the video clear. You could share these videos on WhatsApp. Share these videos with us on WhatsApp. Sure, Dr. Islam, everything will be sent to you in the materials, by the way. I might be a bit late, but I send you the materials because I'm reviewing. There are some things I remove and some I add just to keep the materials rich with you, but it's nothing serious. So don't worry, all these videos are available. I'm bringing them to you anyway. Thank you, Jazana, and may God be with you. And Jazana, and may God be with you. As we were discussing in indirect convergence, I have the coupling device and the thin film transistor. The idea is that I currently have, as we were discussing, a device that receives and emits light beams, which then produces the light photons or emits the light particles of the light beams afterwards. I start by receiving it on the photodiode in the case of thin flat panel or thin film transistor, or I process it on a charge coupling device via fiber optic or the existing sensor. Then I translate it and convert it into a binary system with zeros and ones for storage on the imaging device. As we were discussing, indirect convergence, thin film transistor, photodiode, and scintillator material. The scintillator material converts into X-ray photon. The issue, as I mentioned, is related to the diffusion that occurs, where there is a diffusion of light in many directions or isotropic distribution of light, which always reduces spatial resolution. In contrast, when there is a specific track or a certain path from which you know the light is coming, you can localize the site of interaction more precisely. This is, of course, what led to the idea of having two types of scintillators, like cesium iodide, where the roots are clearly defined in such a way that you can determine the path of the light, unlike what is not included. Okay. And of course, you will find it available, but just so you know the type and such, it will start telling you that, well, there is one, but it's a bit more expensive. Of course, this will be better for you in the machine part, in the imaging part. The second layer I have, the photodiode, which is made from silicon, is generally considered to be a semiconductor material. It takes the output from the scintillation or from the scintillator material and converts it into an electronic signal, such as a current or voltage. So I said, inside the photodiode, is there something called, inside it, there is something that does the job of converting the incoming signal into an electronic signal. In summary, an electronic signal starts here. After that, this electronic signal is received, and each square, which I call a pixel, corresponds to the photodiode, so that every O time, the squares you have occupy the entire exposed area for radiation. So when you look at the detector element or the chips that are present, what is the TFT layer made of? Here you have something called a pixel or picture element, and there is a storage capacitor. This storage capacitor stores the information or the electronic signal that is present, and these pixels receive the electronic signals coming from the photodiode. This is to send it to the computer. As he was talking about the fact that the larger this part is, the more you can increase the amount of information it can provide. Identifying users from users. The indirect is the one that charges the cable.
What is the function of the storage capacitor? Excuse me, where is it? It's the one on the, the data, the electric current is coming down on this pixel. What is the purpose of the storage capacitor and how does it work? I also don't understand the point about the TFT. Quickly.
Okay.
We have concluded that the electrical charge is applied to the TFT.
So what happens next? Great. I have now taken my data from this pixel area and the electronic signal has reached the pixel, right? Okay. So where do I send this electronic signal? I should send it to my system for processing, correct? But shouldn't there be a place to store this electronic signal so it doesn't get lost? What is the place where the storage capacitor usually stores its charge? The function of any electrical capacitor in the world is to store electricity, to store the charge. Once the electricity is stored, I want to send this charge or not. I can control it through the switch. The switch will tell you to send it now or not. This mechanism is what is referred to as the theme film or theme flat panel chronosis.
This situation occurs, but there must be a mechanism in place for this reason. Let's assume today your data is lost for any reason. You need to have a way to store the data.
This happens in no time, doctor, but there must still be a mechanism in this way. Why should we have a storage capacitor? Because we need to store the data. There must be a switch. This happens in no time, meaning it doesn't take long. If you imagine sending a picture and communicating with a digital system, you understand, but you must handle it this way. Okay. Here's the idea. I have a CCD or charge cable device, and I have fiber optic or a lens. The CCD is responsible for transferring the charged or light parse that comes from the scintillator to the sensor chip. The CCD can convert light photons into electronic signals and can transmit these electronic signals to the computer for processing. So once the light photon reaches it, it converts it into an electronic signal and simultaneously starts transferring it from the sensor chip to the computer. Now, this is the same in the direct case. You've removed the scintillation aspect and the scintillator material, but here you have it directly on the semiconductor. The semiconductor also functions such that when an interaction occurs, the charge is negative and the positive charge is what it's on, and you start to have two electrons. I'll show you the image. So I'm getting this from this detail. Is there a difference between TFT and charge cable device? The difference between this and that? Yes. The TFT is considered better than the charge cable device. Why do I prefer it? Because when you are here, if you look at the thin flat, the transistor here is like the chips that are present. It represents the idea of the matrix, doctor. You have every point on the photodiode below, and in front of it, there is a pixel that receives the electronic signal directly. This prevents the idea of signal diffusion, enhances the signal, and allows you to localize the signal from one place to another, which improves the performance. That's why, when they moved to the topic of direct radiographics, they kept the TFT with us. However, the charge cable device will not be mentioned much in the application. It will not be mentioned much in the application. It will not be mentioned much in the application. It will not be mentioned much in the application. It will not be mentioned much in the application. It will not be mentioned much in the application. It will not be mentioned much in the application. Here is this semiconductor, which is amorphous selenium, not amorphous silicon. When X-rays are incident on the semiconductor material, what happens? It starts to generate negative and positive charges, which attract each other depending on the electrodes present. So the negative charge goes to the positive charge, and the positive charge goes to the negative electrodes. This is what happens, or the positive charge goes to the charge storage capacitor, and then the image is formed as we were explaining. This semiconductor topic is now even present in gamma cameras, even in semiconductor detectors. It gives you more resolved images and addresses many issues in the detection of signals. In the past, they used sodium iodide detectors in gamma cameras, but now they have been replaced with more advanced and efficient detectors, such as those that are significantly better. This allows for a better and more effective reduction of the dose, enabling you to obtain a good image with the least possible dose. You can even perform further post-processing and significantly enhance the image afterward. Absolutely not. Under no circumstances, no way, not at all, definitely not. There is simply no possibility whatsoever. It is entirely out of the question, and it cannot happen under any conditions. Film or radiography, whether it is from film radiography to digital radiography. So we are now at the part that remains in this section, which is the part that talks about artifacts. I wanted it to be the last thing, because there will be some related topics like dead artifacts and post-image and things like that. I would like to include some images in the topic to make it clearer, God willing. Correct.